why is searching and sorting an application? Well, because if I gave you a searching or sorting problem right now, I would expect you to just know how to do it. But now we are going to look at how to do it in certain ways that we can have efficient algorithms for searching and for sorting. So let's start with lists, and let's have a simple like the simplest function possible that we could have. Let's say let search x in x's. I have to apologize if I'm a bit confused today because I'm quite ill. So search for x in a in a list of x's and return true if we find it and false if we don't find it. That's essentially the search problem. But the search problem is for an arbitrary data structure. We're doing here for list, which is a simple data structure. And this is something that you not only I expect you to do, but there were assignments back where you had to do some kind of searching into a list to do it. Okay, so just to refresh your memories, I want you to write this function yourself, and you can talk to the person sitting next to you. And I'm only going to give you a few minutes because it's not extremely difficult. But just to refresh your memory a bit. Okay, so what kind of function this is going to be? This is going to be a recursive function. And we have a value and a list, and obviously the recursion is going to be on the list. And we have two cases. And this kind of infrastructure is something that you should okay, can you please be quiet now? So this kind of infrastructure, you should be able to kind of come up with it more or less automatically. And now the first one is the base case, the trivial case. Can we find some element x in an empty list? Can we? Yes or no? False. And this one, let's not clash the identifiers. So this one, well, we can search, the recursive call is going to be searching for x into the tail. But we also look at the current element. Aren't we lucky? Maybe we're lucky and we already found it. So this is in case we found it, and we're gonna OR it with so it's either the current element or we find it in the rest of the list. And this is quite nice because OCaml is implementing the OR operator in a shortcut fashion. So if this argument is true, then it's not even going to bother to search the rest. Yeah? Can you make it slightly bigger? There's three rows here in front if you want to come. Do you want to come? Yeah. Okay. I like the class to be more compact. I'll also make it bigger. Okay. um, you can still come in front if you want. Okay. So this is quite efficient because if we want to search through the list, once it finds it, it's going to stop. If it doesn't find it, then it has to go through the entire list. But another thing that we do in programming quite a lot is generalize. So we start with a function that says, well, this one is searching the list for a particular property. Yeah, it's searching for elements that have a particular property. So let's generalize it a bit. So generalizing is good because especially if you write libraries, well, when you write the program that you're going to submit it as an assignment, or is meant to do something, then generalizing it might not seem so useful. But a lot of the time, people, when you write code, you can write it as a library for other people to use. And then you can generalize, which means to provide more general services into the function. That means your function is going to be more useful. So here, we can generalize by replacing an actual property. So here it's a concrete property, x equal x prime, with a function. A function that applied to something is going to give us true or false. So because we are searching for an element, it makes sense to apply it to the first element. And now this function cannot come out of thin air. It has to be given as an argument. So let's put this into the interpreter. Oops. So x prime. And here again we have to pass the same arguments, obviously. Search f in xs prime. Okay? So you can see the type of search. The first argument is a function that takes an element from the list and tells you whether this property is true or false. And these kind of functions that return true or false are usually called what? Think about those of you who are doing logic, language, and computations. What's a function that gives you true or false? A predicate, yeah. So let's call it P because it's a predicate. Okay, let's put it again in the... Okay, so now you can see this is the type. It was only a variable change. Yeah, so it takes a list and a boolean. Now question. Now I have a general function, and the idea is when you have something general, it still has the same functionality as before, but it added more functionality. So now let's make another function. Let's specialize search above to finding an element x. So let's call it let find x in xs. And I've done something that's more general. So now I should be able, using search, to re-implement find in a much simpler way. So in order to do that, I will need to call search with 2 arguments. So finding is a special case of searching. Finding a particular element is the special case of searching for an element that has a property. So what is the first argument and what is the second argument of search if we want to achieve the same functionality? Let's start with an easier one. What is the second argument? Who knows what the second argument is? Okay, from the back there, what's the second argument? Access. Yes, thank you. It's because we are searching in the same list. Yeah, we don't have to change that. And now we have to give it some function p here. Yeah, we can either define it inline, but we can also define it here. P, it takes an argument. Sorry. Yes. P takes an argument, and then it does something to it. So, what is the predicate that we are searching for? So, in English speaking, in English language, what is the property that we are searching the list for? Yeah. Yeah. So let's say for now that we have, this is not the best way to write it. I'll just write it in line here. So it's a function. It's a function. And the function is going to take, we're applying it to the current, we always apply it to the current argument. And let's call it x prime so we don't get confused. And what is the body of the function now? So because we want to define the property of being equal to x. So how should we write this for some arbitrary x prime? Poppy? Yeah?
Would be x arrow x prime.
X arrow? No, it's just x equals x prime. Well, the arrow means a function, so this is the property. So the property, we have fixed this x because this is the argument of the function. And now, inside here, I'm having another x prime. And I want to see whether this x prime is equal to x or not. And this is how you write it. This is how you test whether some x prime is equal to x. Let's have a quick test. So if we say, for example, find 3 in 1, 2, 3, 4, it's true. Yeah? But this gives us a lot of flexibility. Yeah, this gives us a lot of flexibility because now we can search for something that has any property that we want, not just a particular property. So, for example, I can search. I can search for all the elements in a list that are greater than 2. So it's exactly the same pattern. So for any x prime, I want to see if it has an x prime which is greater than 2. It's true. Yeah? So it's very nice because now here you can put whatever condition you want, and that's going to be, it's going to let you find whether there is an element with that property or not. Let's generalize them some more. Let's change, and also change the functionality a little. Because if you're looking for a particular element in a list, you're really interested whether it exists or not. But now if you're looking for elements in a list that have a property, you may not, maybe you're not interested just in whether they exist or not, but you're interested in whether they, which elements they actually are. And this is a kind of a function that's called filtering. So it's a filter. You have a list, and we're going to select all elements that have a certain property. This is exactly like happens when you do a query to a database. You give a condition to the database, a select statement, and then the database is going to return to you the records that satisfy that property. And you can do that for functions as well, for lists as well. It's a very useful property. And this is, let's call it filtering. So I'm gonna keep this skeleton because we kind of work with the same skeleton. So now we want to, again, this is a function that you know how to do it yourself. I'm not sure if there was one of the assignments that requested you to implement this function, but it might as well have been, because it's something that by now you should know how to do. So if I want to apply a predicate P to filter a list XS, if I start with the empty list, then I get what? I just want to select those elements of the empty list that have a particular property P. What list is that if I filter over the empty list? It is the empty list, yeah, because we're just selecting. If you select from the empty list, you're going to get the empty list. And now, when you look at a list that has a head and a tail, the question is obviously whether the head, x prime, satisfies that property. If it satisfies that property, we're going to include it in the result. Otherwise, we are not going to include it in the result. So the key test is whether P applied to x prime is true or false. So because this is already a Boolean, I don't have to say equal true. So I'm testing x prime with property P. And if it's true, I just want to keep it. Otherwise, I don't want to keep it. And here, in both cases, the recursive call will be just filtering the rest of the list. Okay, so now let's take this thing that we did here. And instead of searching whether there are elements greater than 2, we can filter. So this will give us all the elements that are greater than 2. And it works, see? It filtered the list. And it's very general. We can give it any condition here. It's going to find those elements that satisfy that condition. Now, I said this is another generalization. So how do we implement this? This time, how do we implement find x in XS in terms of just filtering the list? let's do it in 2 steps. Let's refine first searching, which used to give you only true or false in terms of filtering, because that's what it means. Filter is general, is more general. Whatever we did with search, we can do with filter. So how do we do a search for property P using filter? So what is filter going to return to us? All those elements of the list that satisfy P. How can we tell from this whether there were any elements of the list satisfying P or not? Yeah, if it returns the empty list, it means that it couldn't find anything. So we can test its size. So we filter it, and if it returns the empty list, it means it hasn't found anything. So search, sorry, P. So for example, if I say search 1 in the list 1, 2, 3, 4, oh, I have to give it a predicate, of course. So we know how to make this into a predicate. It failed. Because here, what's the error? Quickly. So I say it's true if it returns the empty list. Is that what I want? No, that's when it's false. So I did the opposite of correct. The opposite of correct is easy to fix. Nonsense is hard to fix. The opposite of correct, we just change that from equal to not equal. So now, does it work? Now it works, yeah? So you see how nice and how nice and beautiful it is, because you can take something that's simple and generalize it and make it into something more flexible. And that thing that's more flexible, you can use it. And the question is there going to be any difference? Let me think if you can think quickly off your feet. Is there going to be any difference between searching, implementing in terms of filter, and the previous search that we, yeah? This is why? Yeah. So this one always goes through the same list. It has to go to the end to do the filtering, whereas search, it always stopped when it found the first element, and that's a very generally kind of valid lesson. Whenever you generalize something, you can do something that's more elegant and more concise, but you're always at the risk of introducing inefficiencies. And this is one of the big trade-offs that you do in programming all the time. Choosing whether something you want it to be clearer and easier to get right, or you want it to be more efficient, case in which can be more complicated to do. Okay, let me see. I don't. Okay, we have plenty of time. Yeah. So now, using just this filtering function, which was the generalization of searching, we can define a sorting function. Again, sorting is something that you should have been, if I just ask you before this lecture, write a function that sorts a list, you should be able to come up with something. Maybe not the best thing, but you should be able to come up with something. But now we're doing in a more pedagogical way. We're doing in a kind of a step by step. See, I'm trying to tell you a story how I started from search, and you're going to see there's a bottom line. There's a punchline to the story. You're going to see next lecture. But for now, we can do sorting. Sort. This is what we want to do. So pay attention, because I'm going to try to derive this function, which is quite complicated. Probably if I let you to your own devices, you would come up with something that's fairly complicated way of sorting a list. But now, if we have filter, which we just defined here, see, this is a standalone function. This has not been defined in terms of anything else. But just with using filters, we can define searching very, very easily. Sorting very, very easily. Let's alternate between the syntaxes so you don't get bored. So by the way, sorting, I didn't explain what it is, but it's just the intuitive thing. It's like you take a list and you arrange them in increasing or decreasing order as a sequence, with the smallest first or last and the largest last or first. You can have increasing or decreasing sorting. Sorting the empty list, is that hard? Is that a challenge? No, that's the empty list. It's pre-sorted. So now if we have filter, let me just bounce off of you an idea. We know what the head of the list is. So why don't we so I'm going to write it informally here. This is not OCaml. Everything larger than X, sorted, and then this is going to be a list, and then followed by X, and then followed by everything less than X, sorted. Yeah, so we have a selection function, filtering, and we can use the head of the list to figure out all the elements in the list which are less than that, and all the elements in the list which are greater than that. So we you split our list in two. And now we can make a recursive call, sort the first part, make a recursive call, sort the last part. And now if we think about X as a pivot, everything that was to the right stays to the right, everything that was to the left stays to the left. Okay? So when I say everything larger than X sorted, I really mean that first we select everything that's larger than X, then to get the sorted version, we call sort on it. Okay? And maybe we are going to need some brackets here eventually to get syntactically correct. Okay? So that's the general idea. Now how, using the filter above, this filter, how can we select everything that's larger than X, and how can we select everything that's less than X? Okay? So I told you we use the filter, so it's going to be filter something something, and everything less than X, it's going to be again filter something something. Okay? So what are the arguments to filter? What's the second argument to filter here? Where are you going to select these elements from? From the tail, yeah. So in both cases, we select from the tail. And in both cases, we want to give a condition which takes some x prime and some x, let's do it like this, I don't want to, let's do it in a very step-by-step way. So here, we want to do this and this. Okay, so let's not be intimidated, because if we make a mistake, we can fix it. I'm going to move this on the, let's do it like this, so it's lined up more nicely and is not so long. Right, so we need here a function that is going to help us select all the elements that are less than x and all the elements that are greater than x. So we say that this function is applied to some x prime. Yeah, we don't know the x prime. We just want to define a property that can be applied to any integer. So how do we select here everything that is less than x prime? So what's the, sorry, everything that's less than x, because we're operating relative to this x. So what should be the condition here? It's very similar to somebody else, very similar to what we did before. So we want to say that if x prime is less than x, what could it be? X prime is less than x. How about here? X prime is greater than x. So the first thing to do, let's see if it type checks, okay? Yeah, it does. So this is our, let's get this out of the way, because I want you to, it's not going to be, this is not going to compile like this, but I just want you to look at this and, you know, appreciate, you know, the prettiness of it. It's a sorting of a list that you can write in just in a few lines, of code. So if you think you can do better than, yeah.
Well, I worked on lists with unique elements, so you need to change one of the conditions to either less than or equal to.
Yeah, I was gonna get there, but I just want to do a little bit testing first, and so ask questions if you put your hand up. Don't give away the ending. But yes, that's true, because okay, so it's true. So let me show you an example where this is true. Sort 1, 2, 3, 4, 4, 4, 4, and it says 1, 2, 3, 4. Oh no, what he said is true. So why is that? Because we are partitioning everything that's less than strictly, one that's less than, greater than strictly, but what happens to the elements that are exactly equal to x? Where should we put them? Well, it turns out those elements, it doesn't matter where you put them. So, I mean, if you really wanted to be very pedantic and you want to have the same pattern, you could select here all the elements that are equal to x, and then that means, but that would be just too much work. It's much easier to just put them either on one side or the other. It doesn't matter. So let's say we put it here. So yeah, it works. And now it's correct as well. Okay? So this is our first sorting program, done in just a few lines of OCaml. And the way we derived it is by kind of starting from the idea of searching and then generalizing twice, first in terms of the condition, then in terms of the argument, until we came up with a function that's very useful, filtering. And now it turns out that sorting, it can be expressed immediately in terms of filtering. There is, however, no, it's okay. So, and this is an algorithm that if we wanted to prove correct, it would be fairly easy because, as you can see, it's a structurally recursive definition. So it's a definition of the algorithm that is guaranteed to terminate by construction. So a lot of time when you write if you write your own sorting algorithm and you start playing with for loops and while loops and switching things about and having some kind of a condition that you test, then you have to prove that your algorithm actually terminates, that condition eventually will become true. And that is not trivial. Whereas here, this algorithm, at least the termination of it, is trivial. And next lecture we're going to look at, even though this is a nice and correct algorithm, this is not an efficient algorithm, and we're going to come up with an efficient version of it. Thanks.